I promised in the last slide that we would have some electrical terms that'll help us understand that glowing tube, that Teltron tube, that showed us how the electrons flowed and coming up with mass to ratio. We're trying to measure the electron after all. And to do that, we need to have some terms. And I thought about my viewing audience and I thought, well, maybe I better go backwards and come up with some basics, and then we can talk about the actual instruments there. Basic unit of electricity is charge. Charge that is not moving, and we call it static electricity. Static electricity is what happens when you, sometimes during the winter with real low humidity, you rub your feet across the carpet and touch a metal object and it sparks, or you touch another person and it sparks. Before that spark, you had a static charge on yourself, and the static release of charge in the sky is lightning. So the charge has a lot of power that's going on there. Now, charge will be represented as Q, and we can do some experiments that show what the charge force is between those, and something called Coulomb's law. The next thing that I want to bring up is voltage. Voltage is the potential to move those charges. And sometimes it's called electromotive force, but usually it's represented as a big V in the math things that we will do. And that V is voltage, the potential to do things. For instance, your outlet is 110 or 120 volts, however you want to quantify that, but that is the potential to do something. Unless you connect those two prongs together, nothing's going to happen. And obviously you don't want to hold on to both prongs of that outlet, or you might get electrocuted, mainly due to the 60 hertz that'll go through your heart and interrupt that, but still you don't want to do that. Now, what happens when you plug in a hairdryer? Plug in a hairdryer, and the ability of that potential moves the electrons in that cord and up through that heating element of the hairdryer. And what's going on? What do we call that when those charges are moving? Not static charges, but we call that electrical current. And the current measurement, or the current symbol that's used, is A for a scientist ampere. So we measure current in amps. You've probably heard amps. And we measure potential force for that current as voltage V. And then when we talk about the power output of that, we talk about that in watts, usually W. So you go by your hairdryer, it says 1500 W, 1500 watts. You can figure out how much current it's created from that voltage to come up with the watts. Okay, something else we got to talk about. We have to talk about the magnetic fields, because in this experiment we're going to use a magnetic field to affect the motion of the electrons. The magnetic field is, in this case, created by passing current through coils of wire. In that last one I talked about the Helmholtz coils, but that current, once it passes through that coil in a circular manner, it creates a magnetic field that goes at right angles to that current path. The magnetic field is measured in oersteds, I believe that's correct, but it's usually represented as the capital letter B. So we've got B, here's a quiz. We've got B for the magnetic field, V for voltage or potential to move those, Q for, did I already cover Q? No, Q is for charge, and I is for current. Q for charge, V for voltage, I for current, B for magnetic field, and I think that we've covered everything so far. Once we get into the diagram next, we can look at those pieces and make some sense of it. And then, unfortunately, it's time to do some math on those things, to do some calculations with those values. If I've missed a value along the way, then we'll fill that in as we go. Here's the diagram. And as you can see, there's a round thing here. This is the Teltron tube. And we should be able to start making some sense of what's going on as far as inside the tube. Notice we've got some letters here. There's a little E. Little E stands for the electron. This B is a magnetic field, and the magnetic field is going as if it was going into the paper, and that's why you see the not the point of the arrowhead, but the tail feathers of the arrow. That's the way they do that, so they show you which way the magnetic field is going here. You can't, in other words, it's not 3D, so we have to imagine that it's going into the paper. E for an electron, R just happens to be the radius. If you remember from the picture, the electrons go around in a circle, so this is the radius of that circle. The V, this little arrow here, that's the direction that the electrons are moving, and the V is for the certain velocity that those electrons are moving. Couple little things down here. We've got a cathode. You know, wires. Where are the wires? Well, the wires come in later. They'll show you that in a little bit here. The cathode is the negative side of the voltage. Remember, the voltage is the potential to move charges. The E is definitely a charge. So we move the charge from the cathode to the anode, and we put a high voltage between those. In this case, it's not super high, but it's 200 volts. 200 volts, and I'll have to use another term here, direct current. 200 volts means that it's not alternating current like what comes out of your outlet. Let's scroll down here a little bit. Here's our first formula. 1/2 mv squared equals E times V sub A. What is this all about? Well, 1/2 mv squared, this goes back to some physics. This is the kinetic energy of the electron. We're just talking, remember, we're trying to get the electron and we're trying to measure some mass and stuff like that. The M is for the mass of the electron. The V is not big V is voltage. The little v is velocity. And if you take 1/2 mv squared, you get the energy of an electron. Another way to get the energy of the electron is to take the difference in the voltage from anode to cathode and multiply it times the charge of that electron. And this is called an electron volt. The electron picks up energy when you have a voltage. You increase the voltage, then this gets a higher energy to that electron, and that is moving the electron. So kinetic energy is moving. Here's the 1/2 mv squared. Let's scroll down a little bit. Let's see what we got. On that diagram, we had the R. Let's go back quickly to the diagram so you can see what that R is. The R is the distance from the center of one of those coils, and the magnetic field is going it's going at right angles to the rotation here, and it's going as if it was going into the paper. You can think of that one. So let me go. Let's don't lose our place here. Here's the R of the radius. Here's the mass of what? That's mass of the electron. And this is V squared. So something disappeared here. What happened to the 1/2? 1/2 mv squared. I guess we'll just have to trust this thing, that the energy of the electron volt times the magnetic field, which is B. Oh my. Where did we get, how did we get from here to there? Okay, let's read this thing. The magnetic field of Helmholtz coils, can't talk right now, is perpendicular to this velocity and produces a magnetic force which is transverse to both V and B. Magnetic field perpendicular to the velocity, which is transverse to both V and B. The force created is going to be, the force. Okay, if the electron's not moving, then we don't have the force on it. So the electron times the velocity times the magnetic field creates a force, and that force is towards the center of that circle. So even though the velocity is going at right angles to that, or tangent to the circle, then this force is bringing it in. This centripetal force is a force towards the center. Gravity that holds the moon is a centripetal force, makes an electron move along the circular trajectory. The radius of the trajectory r can be found from the second Newton law. Let's see. Force equals mass times acceleration. Force equals mass times acceleration. Okay. This side is supposed to be EV times B, which is the force, and this would be the mass times the acceleration. Let's see. How do we get V squared over R to be the acceleration? V squared over R be the acceleration. Let's see. I don't follow that exactly. What's going on here? V squared over R, is that supposed to be the acceleration? Oh, it is. That's the centripetal acceleration. V squared over R is the centripetal acceleration. The centripetal acceleration is given by V squared over R. Whereas if it was just going in a straight line, that would be how fast it's speeding up. Well, here it's not speeding up, but it's called acceleration. If the arrow starts changing direction, then that arrow starting to change direction is considered an acceleration, change in velocity, not in magnitude, but in direction. So Now I actually even understand that. That's looking pretty good now. Okay. EV. Now let's see. From this equation, we obtain the expression for the charge to mass ratio. Boy, we're really close. There's a misprint here. Ration. It should be ratio. Expressed through the experimental parameters. Let's see. Here's E over M. Let's see if we if we divided both sides by M and then divided both sides by V over B, V times B, don't follow. Don't follow. Oh, if we divide by, this apparently is the velocity. This little v is the velocity. That's what I said it was supposed to be. So that's also the velocity. The electron times the velocity times the magnetic field gives us the force. So what's going on here? Let's see if we do the math. Can we do that in our heads? I'll give it a try. Like I said before, the m is in the denominator. So if we take m and divide both sides by m, the m disappears here. All we've got is v squared over r. Then we divide both sides by VB, then we've got R still in the denominator, B in the denominator, and the V in the denominator here cancels this out to be a single V. So the algebra, maybe I should do that on the sketch pad, but anyway, I see where they're getting. Here's the charge of the electron in coulombs. We didn't mention that the units for charge are in coulombs, and I did mention Coulomb's law. Let's see. We shall calculate the magnetic field using the Biot-Savart law for the current loops of the Helmholtz coils. Oh my gosh, what's this going on here? We got all kinds of numbers that I don't know how we justify that. And here's a bunch of other stuff. Well, let's look at what we do know. I, that's current. That's current. So I guess what they have here is a little, let me make that a little bit larger here. Oh, that's helpful. This law here, B equals 8 over the square root of 125. Where does that come from? Anyway, the current here, I'm going to guess that HC is the current through the Helmholtz coils. N is how many turns of wire you have. You've got more turns of wire, that's going to create a greater electric field. And little bitty, this mu, which is a Greek letter, mu sub 0 is what's called the magnetic permittivity of the air, or permeability. Permittivity is in another area, I think, with capacitors. But anyway, that mu sub 0 is the permeability, and it's given by this constant value over here, 4 pi times 10 to the minus 7 t, which is the measurement of, boy, we're getting into a lot of stuff that I need to understand. Let's see. Remember I said this is Larry the Learner. He's trying to learn as we go along. And all this stuff, oh man, where does all this go? Then they plug in this B value, which has all these numbers. You plug that into the B. Wait a minute, how'd that get to be 2VA blah, 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 125 and a square or something. And we better do this math on a sketch pad. I can see that I don't trust my ideas here. This says the potential. Okay. V. Anyway, let's go back to what was easy. Accelerating or the energy that's picked up by the electron has to do with the voltage applied. Then we've got this. So I'm going to close off this video because I'm getting kind of lengthy here, and we'll start with some math for the next piece and prove all this stuff out on paper. That's what you have to do here is until you can believe it, you're not going to trust the numbers that you get out of it.